ME204, Impulse and Momentum, Rigid Body Kinetics. We've already determined what impulse and momentum of a particle is like. We have linear or translational momentum, which is a mass times a velocity vector. We have a linear impulse, which would be a force vector times a change in time. We have angular or rotational momentum, or something that we would call a moment of momentum, which is a mass times a velocity vector crossed with a perpendicular distance vector. And we have an angular impulse, which would be a force vector crossed with a position vector, a perpendicular position vector, times a change in time. The same principles that we used for impulse and momentum of a particle can also be used for translating rigid bodies. So let's look at linear impulse and momentum versus angular impulse and momentum. We've already established these equations. For linear impulse and momentum, we have a mass times an initial velocity plus a force times a change in time equals a mass times a final velocity. And if we have a changing force, we have a mass times initial velocity plus the integral of the force with respect to time is equal to the mass times the final velocity. For angular impulse and momentum, mass times a velocity times a perpendicular distance, or a moment of momentum, plus a moment times a change in time is equal to the mass times the velocity times the perpendicular distance, or the final moment of momentum. If we have a changing moment with respect to time, then we simply integrate our impulse portion of the equation as the integral of the moment with respect to time. Again, these same principles can also be used in solving problems for rigid bodies that are translating. So let's look at what the steps are for solving translating rigid body impulse and momentum problems. First thing that we want to do is draw the initial kinetic diagram showing the velocities or the momentum located at the center of mass. Here's an example. If we have a rock that's translating, for a kinetic diagram, we would have mass times a velocity drawn at the center of gravity. Second, we're going to draw the free body diagram and show all the forces acting on the body and draw those forces at the location where they act. This is very important when it comes time to take moments. So if we had an applied force P, then our free body diagram would look something like this, with our force P located at a position HP from the bottom of the rock and XP from our center of gravity. We would have a weight that's applied at the center of mass, or the center of gravity. We would have a normal force that's some distance xn off from our center of mass. And then we have a friction force occurring at the bottom of the object. Third, we want to draw the final kinetic diagram showing the velocities or the momentum located at the center of mass after the process is finished. So in this case, our final momentum would again be drawn at our center of gravity, and it would be mass times the velocity 2. The fourth step is to write a system of impulse and momentum equations using linear and angular momentum equations. So our initial kinetic diagram plus our free body diagram gives us our final kinetic diagram, and we can look at this in terms of x direction, y direction, and for summing moments. In the x direction, we would have our kinetic diagram, mass times the velocity, our initial momentum, plus the forces in the x direction times the change in time. In this case, it would be P, our applied force, times the cosine of theta, minus the friction force times the change in time, is equal to our final kinetic diagram, which has our final momentum, mass times the velocity 2. In the y direction, there's no motion. So, from our kinetic diagram, we have 0. There's no momentum in the y direction. Plus our forces that are being applied, a normal force minus the weight, minus the component of our applied force, p sine of theta. We would have a change in time in there as well, but note that if I put a change in time in there and divide that over to the other side, then that eliminates the change in time, and we're left with simply a static equation. Then let's take a moment about the point A. In this case, from my first kinetic diagram, the moment of the momentum is the mass times the initial velocity times its distance, perpendicular distance from A, which is h sub g, and that would create a negative moment. Then, moving to my free body diagram and calculating the moments times the change in time from that diagram, we would have the applied force P in the x direction, which would be P cosine of theta, times its perpendicular distance from A, which is h sub p, times the change in time, and this would create a negative moment, so we have a negative sign. Then we would look at the y component of the applied force, and this is going to create a positive moment, so we would have P times the sine of theta, times its distance from A, which is x sub p plus x sub n, times the change in time. Then we would also have the moment caused by the weight, which would be the weight times the distance x sub n, which is the distance from the normal force to the center of mass, times the change in time, and this also would create a positive impulse or a positive moment times change in time. All of that would be equal to the moment from my kinetic diagram about the same point, which in this case would be a negative moment of momentum, so negative mass times my final velocity, times the distance from A, perpendicular distance from A to my momentum, which would be hg. Then once we have that, we can solve for the unknowns. Let's look at an example. Same example as what we just wrote the equations for. So we're going to use the same equations, but let's put some numbers into the problem. We have a 20 kilogram rock. It's being pushed by a 100 Newton force as shown. It starts from rest, and we want to know how fast the rock will be traveling after 10 seconds. And our coefficient of kinetic friction is 0.3. So we draw our kinetic diagram, and our initial kinetic diagram is simply the rock. We are starting from rest, so it doesn't have any momentum. Then we draw our free body diagram with the 100 Newton applied force, the weight of the rock, the normal force, and the friction force. And then our final kinetic diagram, assuming that there's no rotation, that it's just going to slide along the ground, is going to have the final momentum, mass times the final velocity. And we know that our initial kinetic diagram plus our free body diagram equals our final kinetic diagram when we're solving impulse and momentum problems. So we can write our equations in the x direction. We have the same equation that we had written on the slide previous. In the y direction, again, the same equation. And about the point A, where the normal force is supposed to act, we have, again, the same equation that we had on the previous slide. Now we can substitute in the values that we know. Initially, my momentum is 0, so this first term is going to drop out because we start from rest. Velocity is 0, so momentum is 0. Then we can put in our 100 newtons for P, and our angle that is being applied is 30 degrees. And we have a mass of 20 kilograms. So we have one equation, but two unknowns still. We don't know what the normal force is, and we don't know what the velocity, the final velocity is. So we go to the y direction equation and put in what we know there. We know that we've got 20 kilograms times 9.81 will be our weight, and we have the applied force P, which is 100 newtons, times the sine of 30 to give us the y component, and we have one unknown. We can also plug in what we know into the moment about A. This equation would leave us with our position of the normal force, x sub n, and our final velocity as two unknowns. So let's go to our y direction, and solving for our normal force, we would get that the normal force is equal to 246.2 newtons. That can then be substituted into our x direction equation, and solving for the final velocity, we get that our final velocity is 6.37 meters per second. So we have determined that as long as this is sliding, the final velocity after 10 seconds will be 6.37 meters per second. But there is the possibility that it could be tipping instead of slipping. So we need to check our assumption. If we put that velocity down into our equation for the moment about A and solve for our position of our normal force, then the position is 0.3 meters, which is less than the 0.65 meters from the center of mass to the point where it would tip. So our assumptions check out and the problem is solved. Our next topic is angular impulse and momentum, rigid body kinetics.